want to let you know, campus that blocks you from fingering.
Wait till the recording starts. Like, just so you know,
I tried it.
campus blocks you from fingering stuff. So you fingered stuff off campus, and you didn't have a problem.
Oh, it worked well.
Wait, did you give him the gift?
It's like, did you guys see the movie Ted 2?
Yeah.
So like, I don't know why this reminds me of this, but you know the what's the guy's name? Qui-Gon Jinn guy.
Oh.
Taken movies.
Yeah.
Liam Neeson. If you've seen the Taken movies, or you kind of know the joke about the Taken movies, that Liam Neeson, like, at what point is it just bad parenting, right? That this kid keeps getting taken. But Liam Neeson has like a cameo in the movie where he stumbles into the grocery store where Ted works. This isn't like a spoiler for the whole movie. It's just like this little part. And he stumbles into the grocery store where Ted works, like all disheveled. And he comes up to the counter with Lucky Charms, and it's like, I have a question about this breakfast cereal. I'm led to believe that, well, no, it wasn't Lucky Charms, it was Trix. I'm led to believe that Trix is made exclusively for children. So, yeah, that's what it says. Tricks are for kids. So, but you understand that I am not a child. Yes, I got that. So if I take these back to my apartment, I'm not going to have any trouble. No, we don't have the budget for that. I won't forget what you've done for me today. I can't. I already have one strike. I have a strike on YouTube. All right, let's pause. We're back.
Next time you use a movie, you should put just a box of Tricks somewhere.
All right. So last time we were, let's see where we left off. We were messing with shared memory, and we had done weights before that. Now we want to look at putting those two things together, right? And then I said I was going to have an impossible homework assignment for the weekend. I distinctly remember that.
All I remember is the coffee I got you earlier.
Well, that doesn't. I think I remember right after you delivered it. I said that doesn't mean you won't have homework.
I said shenanigans. Cancels it out.
You said it doesn't mean we'll have homework. That means you're already assuming we won't.
No, you don't understand. It's like, how do you know we were not going to have homework? Well, because if you didn't give homework, we wouldn't have homework. So, okay, well, how do you know I'm not going to give homework? Well, if we didn't have to do any homework, that means you didn't give us any homework.
He's doing it again. Your Jedi mind isn't working.
All right.
You know, one of these days I'm just going to stop showing classes.
That's true. Tim got a job.
I was just going to let it go and just one day not show up.
That's right. So Milwaukee's newest bricklayer. I mean that in an inappropriate way.
Isn't that pipe layer?
Yeah, nobody knows. Well, that's not appropriate. All right.
Bricklayers, pipe layers, welders.
What? All right, shut up. All right, so last time we built some shared memory that gave us 27 bytes of shared memory, and we talked about the how those bytes are allocated depends on the type of value we wrap it with. If we create an array, we walk that array in integer or char size bytes, for example, and those steps are different size steps. So in our example here, we're creating 27 bytes of shared memory. So we come into main, we create a character, we get our shared memory ID. Here's our key ID. This is what we're going to use to actually store our shared memory, this SHM. So here's where we name our unique memory 5678. Then we go ahead and we create our shared memory segment. So we're going to ask the operating system to get some shared memory, given a key, 5678, and a size, 27 bytes in this case. We're going to tell it to go ahead and create it with permission 0666, Christian worldview. And as long as that gives us something, well, if that gives us something less than 0, that means there was an error, so we're going to scream. Otherwise, we're going to keep cooking. So that reserves the shared memory with the operating system given the key. Okay, so now it's up there kind of ready to go. This has not brought it into the program yet. We have to actually attach to that shared memory. So now we come down here and we're going to attach to that shared memory. What shared memory? The one with this ID. Okay. This says go ahead and you assign the memory location. So if you haven't already assigned the memory location, assign it. We have the parent doing this. This is if it's the first time we're attaching it, it's going to give it'll let the operating system assign the memory. If it's the second, third, fourth, whatever time we're attaching it, it'll hand off the memory location it had previously assigned. Because keep in mind, this is shared memory. So it's not going to just keep creating the memory over and over and over again. It creates it once and shares it. That's the punchline here, right? So, and then this says don't do anything special in terms of flags, giving the default access to it. So shared memory attach is going to return a pointer to that shared memory. All right, and we're going to store that inside of our variable SHM, which is a char pointer, which we can translate into human speak or to C speak or Java speak, I guess we were doing last time, right? As a character array or a string. It's kind of how we typically think of those things. All right, so this is a let's see. All right, so this will get us our shared memory. So from this point forward, assuming we're still kicking, that our program didn't end, we have access to our shared memory through SHM. So we're just going to go ahead and create a character. Well, we already had a char up top called C. We put a lowercase a in there. We went through and we went ahead and filled it up with all the letters of the alphabet. And then we threw in the very last bucket a question mark. Kind of, this is maybe a ghetto way of interprocess communication. We have shared memory where we're sharing data between our two processes, assuming we do a fork. But now we have this extra bucket of that guy that we can use to pass little notes to the different sides of the application. That make sense? Okay. Now we go ahead and fork a child, Abe. We get the process ID. If we're the parent, we're going to sit here and we're going to wait for that question mark. All right, we're going to wait for the question mark and just basically spin. Finally, we're going to print out the contents of that array. Otherwise, if we're the child, we'll go ahead and print that last bucket. We'll change that last bucket. We'll print it again, and we'll notice that the parent also was able to we eventually saw that the parent noticed the difference, that it had become something other than a question mark. It had become an X. Right, so the parent finished waiting. All right, so we'll go ahead and run this again. Oh, this doesn't create a history for us? That's interesting. So GCC SHM ./a.out. So child sees the question mark, child then switched it to an X, child sees the X, parent sees the X. And that doesn't happen until after the parent had finished busy waiting. Okay, so we asked last time if the, I think, was it Abe that asked last time about whether busy waiting was a good or bad thing?
Yes, but angry.
Well, after that, I mean. Well, regardless. So here's a question. Is this a problem? What are we accomplishing there? Effectively, what's happening? Okay, so historically we would call this thing a busy wait loop. Okay, so we're sitting there and we're waiting for some event to occur. Now, we've been introduced to the wait system call. Well, how does the wait system call work? Done. Okay, so we have to think about what's the right tool for the job. If we want to create a scenario where we're bouncing back and forth between two processes. You know, they're performing kind of a dance, if you will, where one process does something and the other process does something, back and forth, back and forth. Is a wait an acceptable use for that? Okay, let me kind of show you what I mean by this. We're going to come in here, and we're just going to use bucket 0 of this guy. We use bucket 0 and bucket 27, so we don't have to redo shared memory. We're not using our shared memory very efficiently in this example. All right. So we're going to go ahead and let's see where we. All right. So we have. Where's my wait loop? Wait loop is right here. This guy. So I'm going to write a little function that's going to take a char pointer in as a parameter. So we're going to just do void wait for. This guy will take in a char val. And then this will be a char pointer. We'll say SHM just to remind us that's going to be shared memory. We'll paste this code in here. Do wait while equal. This will be our val. So we'll call wait while equal, passing it our val, and then passing it the shared memory. We'll keep spinning through here. This function ends when that val finally finishes. Kind of our own wait function, if you will. Okay, so let's go ahead and use this guy just to test it. So we are waiting for a question mark, or wait while there's a question mark. And we'll pass it the shared memory. Just to test to make sure this guy's working. Oh, we got to prototype it.
Does C have a sleep command?
It does.
You just don't want to keep that CPU?
Well, I like stepping one evolutionary step at a time to see how things used to work. That's a pretty pattern I've stuck to for 4 years, haven't I? So we like to see the upgrades to things. So I need to prototype this apparently. All right. So this is what we used to have to do before header files. Actually, just as an example, I'll go ahead and take that guy out of there. We're going to do a, we'll call this guy shm example.h, and we need to put double quotes around that guy. Just to show you the historical fix for this. So I'm going to create another file now. Go ahead and paste this guy in here. And this is going to be shm example.h. All right, so in my header file, I can put all my prototype functions. So this guy ends up being kind of like a summary of what my implementation is going to look like, as opposed to me having just random prototyped functions at the top of my code here. in this case here, having the header file is probably a waste of time because we only had one prototyped function, but that's really where header files were born. Okay, so we've prototyped it up here so everybody's happy, but now our program is reliant on both of these files because we're importing this. And notice when we have the double quotes around our header, that's saying look local. Don't check the systems library for these. All right, so this should work the same way as it worked before. So there's our question mark. We just moved code into a function that makes it more convenient to call. All right, so now, actually kill this. Okay, let's do that. That'd be good. Oh, that's handy. Okay. So we're going to go ahead and bounce back and forth between our parent and our child for counting up through the alphabet. All right. And we're going to use bucket 0 for the current letters of the alphabet, and we'll use bucket 26 for the okay, it's your turn. Okay, it's your turn bucket. All right, so we got our shared memory. Here's where we fork, and we'll go ahead and we'll put inside of SHM at bucket 0 is equal to A, and we'll say SHM at bucket 26 is equal to, why don't we say P for parent. All right, and we'll get. All right, so we're basically saying we're going to start with an A, and then we'll go ahead and say our first player, if you will, is the parent. It's a good reason why I'm referencing it as player. You'll see in your homework assignment. All right, so first player is parent. Now, these things are not indented the same way. It's weird. We'll go ahead and fork. If we're the parent, so we want to wait. Well, we're going to do something first. Got both of these here real quick. All right, so if we are the parent, what we want to do is we are going to go first based on whose turn it is. So I'm going to ask the question, if SHM at bucket 26 is equivalent to a P, then I'm going to say SHM at bucket 26 is equal to SHM at bucket 26 plus plus. Then we'll say SHM, I'm sorry, at bucket 0. Plus plus, that'll go from A to a B. Then we'll say SHM at bucket 26 is equal to C for child. That's if it was my turn. Otherwise, I need to wait for my child to finish. So we're going to call our function down here, wait while equal. And what are we waiting for? We're waiting for it to no longer be a C, passing in our shared memory. If we're the child, well, let's finish the parent. So this will happen one time, right? Now we want to go ahead and loop that. So for right now, we'll just loop permanently. So while true, so we'll steal this. If I'm the child, if it's my turn, I'll go ahead and increment bucket 0 and then switch it over to my parent's turn. And if it's not my turn, I'm going to wait on my parent. Make sense? Well, I'll wait on my parent regardless, but I'll either do something first, then wait on my parent, or I'll just start waiting on my parent. Okay? Now, what we're going to do is after we increment something, we're going to go ahead and print.
Going back to SHM at bucket 0 equals SCH, is that supposed to be SCH?
No. I tested you. What is it supposed to be?
I have no idea.
What do you mean you have no idea?
I'm guessing SHM.
Why is that even a guess? How do we go from I have no idea to I'm guessing as opposed to, hey, you have a typo? What if I say I don't have a typo here? What if I say this is right? What do you think? Is it a typo?
Yeah, it's a typo, for sure. Go back down.
Challenging his confidence in his question here.
Well, you're going faster than me, and you're scrolling, so.
Scrolling. Well, I just want you to read this now.
I just have his up on mine, so I don't have to deal with that issue of scrolling.
Read it! All right.
This is blue.
Oh, wait. Go.
SHM, is that it? Okay. Okay. All right. So both of these guys are going to spin forever. And we're just going to keep bouncing back and forth. What we're going to have each one do is we're going to have them, when it's their turn, I'm going to call this the critical section. I totally did not do that on purpose. I hate all of you. So we're going to go ahead and do a printf. No, okay, so while I'm at this, why did I call that the critical section? Did I just make that up? Or do we learn about that in operating systems? Actually, I think we also talked about it in here when we were going through the initial slides. So we have a portion of memory that's shared between two processes, or memory that's owned by the operating system is how it's more commonly used. It's called the critical section. Where we probably used it in here is where we talked about, if I remember correctly, we were guarding Diet Coke. That was in here? So when we had a semaphore, a bouncer guarding the Diet Coke, the Diet Coke would be considered the critical section. Okay, so that's a portion of memory that we need to control what's happening. So we're going to say that this is the critical section here in our example right here. All right, so we're going to go ahead and printf. What are we going to printf? We're going to printf %C, and we'll say SHM at bucket 0. And we'll do the same thing in both the parent and the child. Okay, so parent and the child both do this stuff. Now, having said that, since this is identical, couldn't we put this stuff inside of the inside of a function or something? Certainly could. We'll leave it here for now. So as forever, the parent's going to say, if it's my turn, I'm going to print out the first current value. Then I'm going to add 1 to it. So the next letter of the alphabet, A becomes B, B becomes C, so on. Then I'll go ahead and inform my child through ghetto interprocess communication, that it's your turn. And then I'm going to sit here and wait on the child. The child does the same thing, except they say, if it's my turn, I'm going to go ahead and print out the current value. I'll increment the value. Then I'll say it's my parent's turn. Now I'm going to wait for the parent over and over and over and over again. So this should go through the whole alphabet and then some. So let's go ahead and run this. Hold on a second.
Did you save it?
Probably not.
Hey. True.
Oh. What is it? While one. We'll just say that. That'll definitely work. I think it's one.
Whoa. Whoa. Oh shit.
Yeah, what?
Look at the top and see how much resources you're using.
Where? Oh, well, I can't. I'd have to run this in the background. We could do that. Oh, we don't really have control anymore.
Control C or something?
No, I'm hitting it.
Hit
Oh
the
my
X on that
goodness.
box. It'll relaunch a new one.
Just exit
Nope,
out
not
of it,
that
no.
one. Oh,
Oh,
uh-oh.
Which box?
It's under tools.
Yeah.
Tools?
oh.
Well, here's a process list. Can I kill something?
Actually, I lied. It was under
Oh my
window.
goodness. I'll look for the one using 100%.
Where's A out? Is it
I think you killed it
oh, it's-
already.
oh, by kill
Yeah, go
when
to-
I closed that thing.
Yeah.
I gotcha.
New terminal.
All right. Yeah, so if we want to see it again, well, I might as well show you how to run stuff in the background. ./a.out. You put an ampersand after that. That'll run this in the background. It'll show me the PID. Woo! Can I not actually?
Nope.
Oh, it is running in the background. Here's the issue. It is running, but you sure want to close the terminal? Close. Go back to window. What I actually need to do is this. ./a.out. I need to redirect standard output to whatever out.txt, and then I need to run that whole thing in the background. Okay, so there's my process ID for this guy, 4487, and now I can go to top, and we can look at 4487.
Oh, it's at the very top. It was like 40, 50%. 60.
Where's it at?
Very top.
Very top.
You're just,
Right there.
Second line down.
Oh,
Third line
Third
down.
down.
all three of those.
Oh, they're all still running?
There's one at 60%, just like half a second ago.
that's not good.
Well, that's not the process ID that came back, though, was it?
Are those the other
You're
ones?
forcing it, so
It said 4487, right?
Yeah.
Uh,
Oh, yeah. I was thinking it was a 3-digit process ID. Yeah, so this is the original parent. This must be the child, and this must be another one that's still going. So now we can kill 4224. We can kill 4490. We can kill 4487.
Does it not update them in real time?
Top is closed. 4487, and now I'll call. Then I'll. Wait, hold on. What did I do? There we go. Oh, there. That's the guy that finally died. So now I can run top, and we should be back. Oh, we still have a 4427.
4227. Yeah, it's 4227.
Oh, 4227.
The C9 guy looking at
Little guy's head's gonna bust. Why are you trying?
Why are they doing a denial of service attack on their own terminal? You know we limit your sister resources. You're the only one this is affecting. Don't mess with me. All right. All right.
That's a big goal, so you can start serving fires with an infinite loop.
So now there was an interesting question there, though, is why? Yeah, why was it all A's?
What is your
Yeah.
A's.
My output file is going to be verbose. Is what it's going to be.
Wait, how many?
It's bigger than allowed size.
Oh, we can.
How many
So
bytes
you-
was that? Go back.
It was bigger than 8 megabytes.
Bigger
that-
than 8 megabytes.
No, there was an actual byte like size.
Oh, did it tell you?
Very large file.
One,
Hold up.
7,
Convert.
Oh, we can just copy it.
Oh, that works.
So there's that number. Divided by 1024, divided by 1024. So that's 169 megabytes. We got this. Hold on.
I wonder if you could use that to.
We're gonna view it. So we're gonna do a more on. This is sluggish. Am I out of am I out of storage? Can I call it out.txt?
Like,
There we go.
This isn't the paid version.
Oh, there's some.
there's
0%.
There's some B's.
It just took it that long to get. Oh, then went back to A.
So,
Whoa.
so go back.
There's
There's
C.
C.
Okay. No, so our code's correct. So what are we seeing here? Explain why it's doing this.
A while loop, it's still printing out the A's, like it's going through that loop while it's waiting for the other thing, like clearly many times.
Okay. Well, so let's show the code here again. So let's just look at it from the parent's perspective. So here's this while loop. This goes on forever. And this says, if it's my turn, do this. Print the thing, update, change it to C. And then I'm going to say wait while it's equal to C. Well, why aren't I able to continue on here? Why aren't I stuck here? We go down to the child one. We're doing the exact same stuff, right? C goes to P, wait on P. In here, we say I want to wait for this character. In this shared memory, I'm going to check bucket 26, and as long as it's still equal to the thing I'm waiting on, I'm just going to keep checking over and over and over again. So why am I getting so many prints? I'm only forking once, correct? So I should just have two processes, the original parent and the one single child. And each of these guys are doing something forever. If I'm the parent, I'm checking bucket 26 and I'm saying, is it my turn? We made it so it's his turn right off the bat. So he says, okay, it's my turn. So I'm going to go ahead and print out the current value at bucket 0. Then I'm going to update the value at bucket 0. And this is in shared memory, right? Then I'm going to update the bucket 26, letting my child know it's their turn. So now I've transitioned out of here. And I'm going to go and wait on the child. So keyword being I've transitioned out of here. That takes time. It also doesn't control when I give up the CPU. So Haxton mentioned something about either sleeping, telling the something to go to sleep, which says, kick me off the CPU now. In this case, we're not. In this case, we're playing the CPU Russian roulette game, okay, which says, I may have just context switched onto the CPU, and I'm going to be sitting here waiting, or I may have just left the CPU, and I actually have created a race condition where I regain control here and print before it's been changed by the other guy. So if we follow this through, so I just printed out our A. So print out an A becomes B. Wait for the child. Now I transition out. Now, in parallel, potentially, certainly if we're running on more than one CPU, if we're running on more than one CPU, the child is saying, wait a minute, is it my turn? Well, if it's not their turn, they're going to wait for the P. As soon as it is that phrasing?
Yes, that's right.
I hate all of you people. It's like walking on eggshells in this class.
Well, I mean, waiting on the C's and all the
All right. Now you're definitely getting homework. All right. So in any case, we are going to wait for the parent to finish. Now, keep in mind, both of these processes could be running on the exact same CPU, or they could be running on parallel CPUs at the exact same time. Okay, so if we use that as an example, if I'm running on a CPU and Abe is running on a CPU, and we're both changing the same shared memory. Go ahead.
Oh, can you run this in the terminal so we can see what it's like on a more powerful CPU with multiple cores, if there's a difference?
Well, I mean, you won't notice a difference.
I just wanted to see Billy
I mean, you're going to be restricted by printing, so
Huh?
you're going to be restricted.
Ah, even a better, well, an additional problem is we've talked in the past that printing is expensive. So how much CPU time does it take to interrupt the CPU, go and print something, and then get the CPU time again? How many times can the other process print before we ever actually get to the next line? So what we actually could have is a situation where after the first time we go through here, this guy should be, in fact, let's just do this on the parent. Just to show what's going on here.
The thing that just doesn't make sense is why it's so many E's. I would expect if it was like stuck in that loop for it to be incremented all the way really fast, but just one of them.
All right, that's actually the child where I'm making that change. Let's just do this.
You have comments saying they're both parents.
That's fine. It's because I copied it.
It's projecting in wants to be a parent.
Where's my, oh, that's the wrong window.
Did you save it?
I think so. Oh, hold on. I think I blocked out the wrong guy. Should be true. That should be false. P. Prints out the character, and let's do a carriage return on this too. I know that's going to get annoying, but that's what we're going to. Actually, let's just put a space. That'll be better. Then we say plus plus. So we're overwriting that memory location with whatever the value is plus plus. Oh, this is actually plus 1. This is plus 1. Here. GCC, SHM, Yeah, stop it. You got this.
Nailed it.
All right, so here's our. Let's see if we get some duplication here, though. Yeah, so we do see some duplication. So this is race conditions. Now, I mean, the reason you get these weird things is because we keep incrementing through ASCII, right?
Okay.
You know, that's why it's we didn't stop at the end of the alphabet. And interestingly, since we're pretty much out of time, I'm still giving you the assignment. Why was this wrong? SHM plus like that. No, I'm asking you that right now, and then I'll give you the impossible assignment. SHM at bucket 0 boils down to a char literal, like the letter A. What is A++? Plus only applies to variables. If I say I++, that increases the value of a variable storing the result back. So this just was improper code. In Java, this would have thrown an error. So it's just +1. All right, so homework assignment is take what we learned here. We're going to create a auto-playing, since we've already learned how to do random numbers, tic-tac-toe game, where the parent and child are playing tic-tac-toe against each other. The shared memory should probably be the tic-tac-toe board in whatever way you want to represent it. And they should go back and forth until there's a winner. And then you declare who's the winner, the parent or the child.
At random. It doesn't matter how they do the X.
Right, they can just randomly choose an open space. Maybe you represent the 8 or the 9 possible moves as 0 to 8.
Or to create 2 perfect tic-tac-toe plans.
Well, you can do that, but I would say don't spend time doing that. Just randomly generate a 0 to an 8 as a move until it's actually a legitimate move. You know, don't let them move into bucket 4 every single time. But, you know, like, okay, here's the legitimate moves left. Just keep generating random numbers until they randomly pick a number between 0 and 8 that hasn't already been picked. Have them randomly play against each other, going back and forth using our busy weights, and then ultimately declare the winner as the parent of the child. Make sense? It shouldn't be too bad, right? All right, we've given you a pretty decent starting point here. All right, I will see everybody on Monday.